flying a plane, but it can be a little bit tricky to understand. So I'm going to try and break it down into kind of a few different steps. There's 5 different altimeters if you're inside of the cockpit of an airplane, which is basically 5 different meters that give you 5 different altitudes. Altitude being how high above sea level you are. There's your true altitude, and there's 4 others. We're going to take a look at one of them known as pressure altitude, and this one here called density altitude. But that raises an important question, because if you have 5 different altimeters, how is that possible? You can't be at 5 different locations from the ground. So one of them, your true altitude, is just how high you are above sea level. Pressure and density altitude give you information about the surrounding air that you're attempting to travel through. So the technical definition of density altitude is pressure altitude corrected for temperature. At the moment, that will make no sense to you because we haven't even discussed what pressure altitude is. But what density altitude essentially takes into account is changes in the density around the aircraft due to pressure as well as temperature. So if a weather front moves in and the air pressure increases or drops and the temperature increases or drops, that's going to affect the performance of the aircraft. And you can use density altitude and pressure altitude to determine whether or not your aircraft is going to perform better, more efficiently, or worse, less efficiently. And that'll impact things like fuel consumption and things along those lines. The more simplistic way to think about density altitude, it is the altitude that an aircraft thinks that it's at. So if a plane flies higher in the air, it's going to experience less dense atmosphere, and it's going to be harder for that plane to fly, or harder for that plane to push through the air. Now, one way is for the plane to physically go up there, increase its altitude, and go higher in the atmosphere. But the atmosphere itself is not just a stationary mass of air. There are weather systems, there are cold fronts, warm fronts, pressure fronts, and some of that air from above can actually wind up getting pushed down to lower altitudes. So you could be flying at an altitude which normally is very easy to fly at, but if some weather system pushes a bunch of, let's call it low quality air down to the plane, it's essentially no different than if the plane had just flown upwards under normal conditions. So that's the idea here. So let me show you how we can start to calculate this, and we'll go through a few. So because air density decreases with altitude, what we would say is if you're going higher in the air, the quality is going to be less and less and less. So if you have low quality air come down to you, it gets pushed down from above, we're going to go ahead and say your density altitude is increasing. So I have this flipped, I apologize. When air from above comes down, meaning that you're flying in air that's less dense, then we say density altitude increases because your plane thinks that it's flying higher up because it's flying in air that's normally located higher up. When air density increases, that would be like if air from typically lower altitudes is pushed upwards, we say that the density altitude decreases, because if you are flying in air that normally under normal conditions would be at a lower altitude, well, then we're going to basically say the plane thinks it's at that altitude. We've gone over this previously, but when you have more dense air, there's more air to push off of. And when you have a lower density air, then there's less air to push off of. So what that means is you'll have more thrust when you have high density, less thrust when you have lower density. So as you travel higher and higher and higher in the air, you're going to find that the plane has to work harder and harder and harder because there's less and less air for those propellers to push off of. Now, again, this is one way. The plane can physically go higher, and it'll now be in what I like to call lower quality air, lower density air, or a weather front can push that air down to the plane. So the plane here in the first case on the bottom left could be struggling just as much as the plane on the top right in 2 ways. It could either bring itself up to that higher altitude, or that higher altitude, lower density, lower quality air could get forced down to lower altitudes. So just understand what you're seeing here is like a normal gradient as you're going upwards, but keep in mind that the weather system is dynamic and pockets of air can move up and down to different altitudes. So we've said this before, as the altitude increases, air density decreases, meaning it's going to be harder for that aircraft to perform. Now, we need to relate everything to a standard, otherwise we can't make comparisons with other pilots or other airports, etc. So what we call the international standard atmosphere is we assume that at sea level, the standard temperature on average is 15 degrees Celsius, and the air density or the air pressure is 29.92 inches of mercury. I should really be calling that air pressure there. So what does this mean? Well, we have something called the barometer, and this is a basic idea of what's happening here. You take some kind of open container, fill it with mercury, and then you invert a tube and you place it on the top. So that's what I've done here. What happens is the exposed part of that beaker has atmosphere pushing down on it. Based on how forcefully that atmosphere pushes down on the top of that, it will force that fluid downward. So I'll kind of toggle this back and forth. That air pressure is going to force some of that mercury into that tube by lowering the height in the open beaker. And we measure that height, how high it has kind of moved up in that inverted beaker. And in this case, we say that at sea level on a standard day, that will rise 29.92 inches into the inner tube of that barometer. So that's what the standard is. Based on the pressure that we typically have at sea level, it's safe to assume that it will generally push down on that mercury with such a pressure that 29.92 inches of mercury will rise into that central tube. Any change in this standard environment is going to affect your aircraft performance. So higher or lower pressure or higher or lower temperature, as we stated previously, is going to have an impact on how efficiently your aircraft operates, and that's what we need to be able to understand. So these equations are all based on standard expected rates of change, and in general, temperature decreases by about 2 degrees per 1,000 feet you increase in altitude. So the higher you go, the cooler it becomes. And then the higher you go, the pressure also gets lower. So pressure decreases by about 1 inch of mercury per 1,000 feet. So we know the standard, as we said, was 29.92 at sea level. If you go above sea level by 1,000 feet, you're going to decrease by 1 inch. You can assume